Okay, so we were looking at this mechanism, right? And we want to know if this preserves differential privacy or not. Exponential mechanism where you had this utility function and right, so you have the utility function, whatever that utility is. It's borrowing terminology from economics, but really you can apply it to pretty much any setting. Like, for example, finding the most frequent item or digital auctions or any other things. Okay. And there was also this notion of sensitivity that we had. Wait, that was important. Yeah, this one. Okay. So we have this notion of sensitivity. So the nice thing here is that even though my original output is supposed to be categorical, I can now define sensitivity. Sensitivity is inherently numerical. So it's not just like I'm changing from some form of cancer to some form of diabetes as the most common ailment, but you're measuring how it affects how the fraction of people with certain ailment changes when you fix that particular. So that allows us to define sensitivity. And the proof that it preserves differential privacy is you just go through the calculations more or less. Okay. So let me do that. It's a little bit tedious, so I'll skip some of them. So how do you do differential privacy? We have to ensure that the answers do not change for two neighboring databases. And as I said, one of the most important lessons that people have learned over the years is that you cannot demonstrate privacy empirically. You need to have a proof, right? And that's exactly what we're going to do. So if you want to show differential privacy, we need to compare what happens when my input database is X versus when my input database is X. So they differ in a single entity. And we want to know what is the chance that I output one particular outcome in either of the two cases. We want these two to be comparable, right? And this, by formula, is some, let's say we had this lambda here. The way to compare these two ratios is to just compare the numerators and the denominators. There's no real sort of cleverness. You just do one after the other. So let's compare numerators. So we want to say that these two ratios are close by. So if I compare the ratio of the numerators, then I get this. But we know this is at most S of u, the sensitivity of X and X prime are two neighboring databases. How much can the utility change when I change one entry? At most, the sensitivity. That was the definition of sensitivity, right? So you get this is at most x of lambda times s of u. And we set lambda to be epsilon over 2s of u. So this is like e to the x of epsilon over 2. And then you do the denominators, same calculation again. If you do the same exact calculation, you get and finally, you just take the ratio. So, and it's really the main novelty here is in coming up with the softmax idea. After that, it's somewhat mechanical to do these calculations. Okay, we had these things exactly. All right. So exponential mechanism does give us epsilon differential privacy. But just getting privacy is easy. I could have always output some constant value and that would also give me privacy, right? So you have to measure how useful is your mechanism. I'm doing softmax instead of max. How bad can my answer be? Okay. And here, the nice thing is that using softmax is usually not too far from the max. So what kind of accuracy does exponential mechanism give? And so the ideal answer, without having to deal with uh, privacy, was so if I had no privacy considerations, given a utility function, I want to find out what P gives me the maximum utility, right? In the digital auctions case, we were interested in finding out which price gave me the most revenue. In the case of diseases, we wanted to find out which disease was the most common across the database. Okay, so this is the ideal answer that we want to compute when I don't care about privacy. Okay. And the nice thing about uh, softmax is that you can guarantee that whatever the exponential mechanism outputs, let's call this Q. We are going to pick some other revenue, some other price, which is not necessarily the optimal, but will have differential privacy. And its value or utility is close to that of differential, to the optimum. Okay. And that's with high probability. So let me write it. Is kind of a messy expression, but it's needed. So there's really not much you can do. We'll parse this in a second. So what this is saying is, whatever your mechanism outputs, its utility is going to be close to the true value with some hypothesis. Okay. Or maybe let me write it in a slightly different way, that it is the utility that you get out of here is at least this much. Okay. So if you want to implement digital goods auctions in a differentially private way, you might pay something in the revenue while achieving privacy. How much do you pay? It depends on, the kind of how many prizes that you have and the sensitivity of the user. Okay. If your function is very sensitive, again, you have paid too much in accuracy. If it's not very sensitive, then you're okay. Okay. Does it make sense? Does it make sense qualitatively? You're saying that, whatever I output, now I have privacy, but at the cost of not getting the max revenue. I might be off from the max revenue a little bit, but how much we can exactly quantify. Exactly. In this case, it's like privacy versus revenue. Okay. And it might seem like a bad compromise, but as I said, companies do implement this because sometimes people refuse to participate. For example, if I say, there's no privacy, I'm not even going to participate. Okay. So depending on your specific application, this might be more desirable than just computing the max revenue. Okay. Yeah. Oh, sorry. That is the number of prices that you have. Number of categories. P is like your threshold, like, how much failure probability you're willing to tolerate. Okay, so T is like, separate parameter. Like, let's say T, even if T is 2, that's like 75% chance. Right, so typically maybe you set it to be 10 so that this is like really e to the minus 10 is very small. Okay, it's like a full distribution, and this exactly gives you kind of the tail bounds. Does it make sense? And the proof of this we are not going to do, but it's basically some kind of Chernoff bound, large deviation bound, or, it's, you just need to use Markov's inequality appropriately. All right. Okay. So, so let's see what all we did, right? So we defined epsilon differential privacy. This was the first definition of privacy, which was kind of rigorous and was useful across other things. And historically, this is called pure differential privacy. Because it was, originally it was called differential privacy, but later on people came up with other notions. So it became pure differential privacy. And then we saw Laplacian mechanism, which is a way to get privacy as long as your queries or your functions have low sensitivity, right? It's not tied to any specific function, but as long as your function has low sensitivity, we can use Laplacian mechanism, right? And then we saw exponential mechanism, which is basically gives you privacy when computing argmax. Right, so if you want to maximize something in a private way, you can use softmax via exponential mechanism. All right. Okay. So let me now discuss something called approximate differential privacy. which relaxes the definition of differential privacy. It relaxes the goal of differential privacy. And so the reason you do that, of course, is to win on the trade-off. So to get privacy, typically we are paying too much in terms of data set and size and so on. So we want to relax it to still get some form of privacy, but with smaller data sets, as we will see. Okay. So to do that, let's motivate the definition by first going back to epsilon differential privacy. So it said for any two neighboring databases, we needed this quantity. Okay. So one downside of this multiplicative definition is that for rare events, you still need this super strong condition. So maybe in some pathological case, this probability is as small as 2 to the 50. Okay. But under this guarantee, under the guarantee of differential privacy, you need to ensure that the other one is also like e to the epsilon times 2 to the minus. The things which are even probabilities which are very, very close to zero, you still need to preserve that, which is desirable in some applications, especially if you want to preserve privacy of rare individuals or rare diseases or something like that. But in some other things, it might be an overkill. Okay. So instead of looking at such a blanket condition, what approximate differential privacy does is essentially puts a lower bound on the events that you care about. So maybe there's a 2 to the minus 50 chance that my privacy gets violated, but that's a chance that I'm willing to live. Okay, so that's what, more or less epsilon differential privacy does. Concretely, we say a mechanism is epsilon delta differential private. You have two parameters now. If for any two neighboring databases X and X prime, and any Y, you start out with the same condition as earlier. Okay. But I'm also allowed to have an additive delta error. So this means, things which are very, very unlikely, let's say I said delta to be like 2 to the minus 10. Then events which are very unlikely to happen, I don't care about violating privacy for that. Okay, does it make sense? So we went from multiplicative guarantee for any event, even very rare ones, to essentially only care about events whose probabilities are at least delta. Okay. So for example, maybe let's say I have my database here. I have my curator. Someone comes in and asks a question, F, and my answer is, okay, with probability delta, return f of x, with probability 1 minus delta, return 0. Okay, so this would be a trivial way to get epsilon delta differential privacy. Now with probability delta, I'm allowed to violate privacy however which way I want. So you're allowing some additive error in the violations. Okay. So typically, in practice, people use epsilon, which is small, but not too unreasonably small. It's like 0.0. But the chance of total failure, the delta, should be much, much smaller. Think something like 2 to the minus 10. Okay, or maybe let's say even minus 20 or something. Okay. All right. Okay. So we seemingly relax the definition. And the first question to ask is, do we gain anything from doing this? Okay, so do we gain anything by going to epsilon delta differential privacy? Okay. And so you can think of this as what's the price of privacy? Right. So in some sense, if I wanted pure differential privacy with alpha accuracy, then maybe I needed my database to have some number of elements. And you can ask the same question. What if I only wanted epsilon delta differential privacy and alpha accuracy? So how big should my database be? Yes, this is the true cost of privacy. So without privacy constraints, maybe I could have solved the same problem with a fewer size of records. But with the privacy constraint, I might need more. And whether or not my privacy is epsilon, like pure differential privacy or approximate, my size requirements could be. Okay. All right. And it turns out that you can actually gain a lot by going to approximate differential privacy. In particular, you can gain roughly quadratic factors for high dimensional data sets. When the dimension is small, there is no big difference, but when the dimension is high, you gain significantly. All right. So let's make that precise. So if I had a function which had k coordinates, then we saw that we can get epsilon differential privacy for it from sensitivity. And the definition of sensitivity was look at all of the k coordinates, how much have they changed between two neighboring databases. Okay. So these were the neighboring something that we did last lecture was we said Laplacian mechanism. Okay, so Laplacian mechanism with this much noise is epsilon differential. Okay. So this is called S1 of S. We define it as S1 of F because you're essentially measuring the sum of the absolute values, right? So if you think of it as a vector, so you have f of x, which is this k-dimensional vector. Okay. And then you had f of x prime. The S1 sensitivity was measuring the distance between these two vectors in one node, right? And in the same way, you can define S2 sensitivity or L2 sensitivity, which is, how much does the output change in Euclidean distance? So for any such function f, I can look at two neighboring databases. What's the distance between these two vectors in two? And in some applications, especially for high dimensional data sets, the 2 norm is a much better metric to use. Right. So for example, let's consider computing the mean, but now I have a database. So we have n users and d features or attributes. Okay, each user has d attributes, maybe one is height, weight, and so on and so forth. Okay. Or it could just be some indicator. Let's simplify it even and say, each one is just indicator of whether or not that person has, let's say, has diabetes or something else. Okay. And let's say I'm just interested in computing the average across these databases. Okay, but this is a real, this is a d-dimensional vector. What's the sensitivity of this function? Any guesses? How sensitive is the mean function in high dimensions? So if I change one entry, how much can the mean change? Well, it can change in each coordinate by 1. Okay. So the total change is at most d over m. Okay. The point or the main point here is that the dependence on the dimension is linear. So that means if I were to use Laplacian mechanism, I need to add noise which is growing with the dimension linearly. Okay. On the other hand, the L2 sensitivity How much is this? This turns out to be square root du. Okay. Again, you can check this by simple calculation. So there are functions, even like this simple natural mean function, which is very sensitive if you think about it in terms of L1 sensitivity. But its sensitivity is quadratically smaller in dimension when it's L2 sensitive. Okay. Right. And this is where epsilon differential, the approximate differential privacy comes in. Just as Laplacian mechanism gave us a way to get privacy for any function which has small L1 sensitivity, there's something called Gaussian mechanism, which gives you privacy for any function with small L2 sensitivity. Okay. So in particular, this is Gaussian mechanism. And the way it works is as follows. It's similar in spirit, except you're changing the distribution for adding the noise. Okay. So for some variance sigma, you sample independent Gaussian Z1 through ZK and just output f of x plus z. Okay. So the only difference from Laplacian mechanism is that we are changing the noise distribution. Okay. And it requires some proof. We are not going to do that. I just need some properties of the Gaussian distribution. But what we can show is the following. The Gaussian mechanism with noise, which is roughly this. So contrast this with, here we said Laplacian mechanism needs noise, which is L1 sensitivity divided by epsilon. Gaussian mechanism is basically L2 sensitivity divided by epsilon, but you pay some parameter which depends on the log. Okay, this is here. Right, the delta is inside the log. All right. So for example, so implies for d-dimensional data sets. Laplacian needs noise, which is roughly d over n epsilon. So for high dimensional data sets, you can get approximate differential privacy while adding less noise. Right? So it's a better trade-off in terms of accuracy versus privacy. but you relaxed your privacy guarantee. Okay. And so this in particular implies that if you want to compute mean to accuracy alpha in each coordinate, then for epsilon, for pure differential privacy, we need n is roughly d over epsilon alpha. For epsilon delta differential privacy, need n roughly. So even to compute the mean of a database, the cost of privacy in the case of, there's a quadratic difference in the cost of. And of course, if I don't have any privacy constraint, I can always compute the mean exact. There's no question about accuracy or privacy. Any questions about the statement? Yeah. So I'm not working through this thing carefully, but basically it's to get privacy, we need to add noise where sigma is like square root d or n epsilon, right? And when you add this much noise, how much error are you adding in each coordinate? Roughly sigma. You have to do a union bound across the different coordinates, right? So, if I add Gaussian noise with error sigma, then basically in each coordinate, I'm changing the answer by about sigma, right? So if I set square root d by n epsilon is roughly alpha, then you can say alpha has to be, like let's say n has to be at least square root d by epsilon, right? Basically it's coming from this expression. You need to use a union bound across the different coordinates, but it's not a big. What is the chance that it's bigger than this? And yeah. Okay. All right. But the really interesting thing about epsilon differential, the approximate differential privacy is comes in its meta property. And this is where I said, it has applications that go well beyond privacy. We started out with privacy. In fact, a whole of this Gaussian mechanism, etc., were introduced with privacy in mind, but later on they found applications which have nothing to do with it. So to talk about them, let's revisit some of the meta properties that we had. Okay, and one of the first things, we had this group privacy. And just like in the case of pure privacy, suppose we have x comma x prime, two databases that differ in maybe k rows. So if they differ in k rows instead of 2 rows, what happens? You take any mechanism and In the case of pure privacy, we said, okay, if you're differing in k rows, your multiplicative factor increases by a factor of k in the exponent, which was a natural thing. And you get the same thing here, except with some additive dependence on delta. Okay, no mystery. You just have to do the same argument where you replace one row at a time and go from one. Okay. Now, just to recall, for pure epsilon differential privacy, we had okay. All right. And the other thing, which we didn't even cover in the case of pure privacy because it wasn't very interesting, but is much more interesting here, is the following. Suppose I have a sequence of sort of databases. I go from some original database to Y1. Okay. And then I have some other mechanism which goes from Y1 to Y2, and then Y2 to Y3 and so on. Okay. This might seem a bit contrary, but it's not really, because you can imagine that, one curator processed the database and in doing so prepared another database. And then another curator is, handling that database and so on. You're introducing some loss in privacy at every one of these steps. Okay. And the basic composition theorem just as we had this here, is if M1, M2, so on up to Mk are epsilon differentially private, then their composition, if I sequence them one after the other, will be k times epsilon differentially. Right. So every time you go from one to the other, the probability factors change by e to the epsilon. So overall, if I do it k times, it becomes e to the k epsilon. So it's k epsilon. And this is one of the reasons why we do e to the epsilon instead of 1 plus epsilon. Because writing 1 plus epsilon to the k is like, you have to do 1 plus epsilon to the k minus 1 and then gets messy. So you do e to the epsilon. Okay. All right. So this is for pure differential privacy. But the same thing more or less works even for approximate differential privacy. So this is called the basic composition theorem. If M1, M2, so on up to Mk are things, then their composition is, k epsilon, k delta differentially private. Okay, so no mysteries. You lost a factor of k, you lose a factor of k, and you lose an additive k delta. Okay. Nothing surprising here. But so the interesting thing is, so this means that you can, let's say I fix epsilon. You started out with epsilon being 0.01. that means you can only do about 100 of these things before your privacy guarantee becomes meaningless. So if you change your database, 100 times, even if you're doing privacy for each step, after 100 times, your privacy is degraded too much. Okay, because k times epsilon is 1, one differential privacy is not very meaningful. Okay. All right. But for the case of approximate differential privacy, there is quite a non-trivial theorem called advanced composition theorem. We're not going to prove it, but I'm going to state it, and then we'll talk about its implications and applications. And it says that if I have a sequence of mechanisms just as before, M1 up to Mk are epsilon comma delta differentially private. And these can be chosen adaptively, meaning I could first decide M1, I can look at the database and then decide what I do next and so on. Okay. Then their composition is actually better behaved. So that's the exact bound, but you should really just think of this whole thing as saying it's some constant times So what does this mean? So it's only square root k times epsilon versus k times epsilon. Even if I started with pure differential privacy, it's saying I can actually do this sequencing roughly 1 over epsilon squared times now before I lose privacy. Okay, so we get non-trivial guarantees for k, which is roughly 1 over epsilon squared. Okay, so meaning earlier, if I started out with epsilon being 0.01, I could only do this 100 times before my privacy guarantee went away. But this is saying, no, that's not right. You don't have to do any change in how you handle the algorithms. But this tighter analysis shows that your privacy, there is still some privacy, even if you do 10,000. Okay. So this is just in the analysis. You're not doing anything to how you're handling them. You're chaining the things one after the other. I can keep changing the database from one vendor to the other 10,000 times, while each time preserving epsilon privacy. And the eventual guarantee is still somewhat better. Okay, does it make sense? The statement at least? Or why it's surprising? Like losing k every, you're multiplying each time with e to the epsilon. So why do you suddenly not gain the k epsilon? And you got square root k times epsilon. That sounds somewhat mysterious, right? Like, why is that happening? Okay. And the intuition, the proof is a bit complicated for this, but the intuition is that it's very difficult to always be an additive epsilon e to the epsilon. You should not be increasing every time with e to the epsilon. Okay. Technically, you should think of it as like, I'm either multiplying with e to the epsilon or like dividing by e to the epsilon. Okay. So if I add k random things, which are epsilon or plus or minus epsilon or minus epsilon, it's more like square root k times epsilon. That's the idea. Okay, that's the high level idea. So you're gaining a lot in privacy by going to approximate differential privacy. This is only holds for approximate differential privacy. If I want pure privacy, I have to pay the k times epsilon. I cannot do it more than a few times. But if I'm willing to go from approximate to approximate, I can lose some. All right. Does this statement make sense? Okay. So, when this came about first time, I think it was very surprising. And after that, people found many applications of this. And one of the applications was to what's called adaptive data analysis. Okay. And what is adaptive data analysis? So imagine, this has nothing to do with privacy now. We're just talking about a problem that arises in statistics across many applied sciences and so on. Right? So think of some kind of, some field where you're interested in collecting some demographic information or answering some questions about some population. I mean, it could even be some bioinformatics application, but let's stick to this. And you say, okay, can you tell me the average age of the people in zip code 90024? Okay. If you want to do that, maybe what you'll do is survey some random set of people and use that as you query and use the sample to estimate the average. Okay, so you query and you get an answer. So the thing that happened here is that first I sample some number of people, collect their statistics, and then every time I query, okay, tell me the average age, you come to the average age. And so on and so forth. And this happens a lot. You can always query and answer and so on. Okay. And in statistics, people study how big should this database be for you or your sample size be for you to get some good certainty in the answers that. Okay, this is like statistics 101. If I want accuracy like epsilon, you need roughly 1/epsilon squared samples in your data set. Okay. If I want to know the average income to accuracy epsilon, I need maybe 1/epsilon squared samples. Okay. Yeah. So we did the sampling already, right? So actually, maybe, if you think of sampling people, it sounds a little bit like, why can't I just always go and get more samples? But think of it as like, I want to know what fraction of people actually have a specific gene type. Subsampling. So the database that I'm drawing here is already a subsample. Okay. So there's an overall population. Okay. That's a very good question. So let me change the example a little. There's a whole population of LA, right? And I'm interested in knowing some sort of genetic information. So I cannot sequence everybody, right? I draw a random set of 1,000 people and then sequence them. Now I have the sequencing data, that's my database. Right? And based on that, I can go and query, okay, tell me, what fraction of people have this genetic marker? I get an answer. What fraction of people have this genetic marker? I get an answer and so on. Okay. So there are two things that we would like to understand, especially from a statistical sort of confidence interval or certainty perspective. One is, how accurate are the answers to each query? Okay. And within some probability, like let's say 90% confidence, I want to say my answer is within some error margin. And the other question, which often gets ignored, and that's how many studies actually get flawed and then get retracted and so on, is how many questions you ask. Okay? Because the sample is fixed ahead of time, right? I did not sequence many people. I sequenced 1,000 people. I asked one question, I get an answer. I asked another question, I get an answer. So there may be a chance that you're interested in the probability that all of my questions I had good certainty. Okay, so I have to take that into account. If I keep asking questions, at some point, I will fail. The sample might not be a good enough sample to get good accuracy. Okay, does that make sense? No, yes. So this trade-off between how many questions I'm asking and how accurate are the answers. Yeah. So basically, I want to know, you have this table, let's say, right? Their genetic information, and I say, okay, how many people have this specific gene? Okay. And I say, next question is how many people have this other gene, right? And so on and so forth. Okay. So, we want to quantify. So let's say I say I'm going to ask 1,000 queries and I want accuracy 0.1 for each query. How many samples should I draw? Right. So this is, so let's fix the accuracy parameter alpha. And let's say the queries are, maybe this is alpha. The queries are, I'm going to make K queries. Okay. So if I want all of my K questions to have good answers, okay, so this is the kind of question that you would like to ask. If I want to make K questions and to accuracy alpha, how many data points do I need? Okay, this is well understood in statistics and so on. But the problem is, people often misuse these bounds very tragically in some cases because the standard bounds apply only if these questions are non-adaptive. Okay. Meaning this is how people get all this sort of flawed analysis where I take a sample of 1,000 people, let's say, then I ask, okay, how many people here have certain particular gene? And then based on that, I'm asking the next question. This is called adaptive data analysis, right? I figured the size of this study, right? I drew these people, I measured something, and now I'm trying to see if something is present. I'm trying to identify some kind of p-value or any such hypothesis, right? And if the questions are adaptive, you have to be extra careful. Extra careful meaning if the questions are adaptive, you're using your sort of sample things, your study, to estimate some population statistics, right? So, maybe I sample these people and say, okay, how many people have the name Raghu in my database? If the answer is 1, then I say, okay, tell me something else. Okay, that's an adaptive question. Like, how many people have last name Meka? Okay. So I decided to ask the question, how many people have the last name Meka based on the answer to the question, how many people have the first name Raghu in the database? Okay. Now, okay, it said there are, 1 in 1,000 people have the last name Meka in the database. Does this mean that the overall population has a 1 in 1,000 rate of people with last name Meka? No, right? Because I had this adaptive thing which created a bias in the estimate that I'm making. Does it make sense? Yes or no? Okay. Right. So because it's adaptive, the second question's answer might not be a good overall estimate across the entire population. Okay. Right. Right. But you can still say, I'm still estimating I drew 1,000 people. And in the 1,000 people, there's one person with the name Meka in it. Right? So what's wrong with that reason? Right? So the mistake is, it is true that if you see Maker in 1 in 1,000 people have that, the estimate might still be okay. Your accuracy alpha might be okay, but your confidence bound should degrade. Because I only decided to ask the second question after seeing the answer to the first one, right? And one of the ways this gets abused in some studies is like, for example, you keep asking this question of, let's say, I want to know, okay, what fraction of people are experiencing some symptom? Like, let's say, what fraction of people are feeling, let's say, depressed? I keep asking this question, but then I stop when the answer crosses something. Now, this is also an adaptive process. I'm deciding when to stop asking the question based on the previous answer. Okay. So this is adaptive data analysis. And people have different set of tools to address the confidence bounds. Okay. And the punchline, which we are not going to discuss, but it's a very important application. It was a paper in the journal Science. Is they use techniques from approximate differential privacy. Uh, okay, so for adaptive queries, maybe let me say it differently. Okay. So if queries are non-adaptive, okay, the queries are non-adaptive, then the size of the sample required is roughly log k over alpha squared. So remember, I want alpha accuracy and I'm asking k questions. I want to know, okay, what's the average, let's say, what's the fraction of people with this specific gene 1, with specific gene 2, gene 10, gene 11, and so on, right? If they're non-adaptive, meaning I decide ahead of time, tell me what fraction of gene 1, gene 11, gene 15, and so forth. Okay. So these are decided before I see the answers. If I want good estimates for all of them, the number of samples that I have to go into the population and I collect is roughly log k over alpha. And this mistake happens a lot in polling as well. Like, let's say I want to know what fraction of people are going to vote a certain way in some election. If I want accuracy 0.1, I can pick roughly 100 people at random. And as long as they're completely random, I can get a good accuracy in how the whole population is going to. Okay. But then if I'm asking adaptive questions, right? I ask, okay, who are you going to vote for? And then I ask, okay, what is the most important factor that is helping you decide to vote a certain way? That's an adaptive question. Okay, does it make sense? So when you start doing this, you need bigger and bigger samples to get good accuracy. So if queries are adaptive, then size of the sample needed is roughly k over alpha squared. Okay. So the number of sample points that you need grows with the number of queries that you're doing. Okay. And what this paper in Science Journal suggested was we will use epsilon delta differential privacy so that we can support k adaptive queries. Size of the sample is only square root. Okay, it's only square root k over alpha. So this prevents something called p-hacking, where this what's called p-hacking in statistics literature, where you try to make up a hypothesis based on interacting with the database and then say, okay, this is true across the whole population. Okay, does it make sense? Like, yeah, you keep asking these queries. In the end, you are getting an estimate for some quantity, but the way it generalizes to the whole population is no longer valid because you are doing this adaptive queries. All right. And what this paper suggested is the way to do more adaptive queries with the same sampling size is the following. Whenever you do this answer here, we're not going to tell you the exact answer. I'm going to give you answer plus noise. Not because you want any privacy or anything, just so that you cannot hack or do some very fine-grained tweaking to get the desired outcome that you. Okay. And this is massively useful for all kinds of experiments, because that means that I can answer k queries now or k different questions for only quadratic for square root case size. And when you're talking about, sequencing people or even more complicated things where drug trials and so on, this is massive savings. Okay. Does it make sense, at least at an intuitive level? So for example, let's say I want to know the efficacy of a certain drug. Then traditional theory says you need to make a trial on, let's say, 100 people to get accuracy of 0.1, like let's say 1 over alpha squared. But then maybe it's a course of things that you have to do. Meaning, if the first stage succeeds, then I do the second stage. That succeeds, then I do the third stage. Right? That's like adaptive queries. Okay. So that was one very cool application of differential privacy, where they said, I know you don't care about privacy here, but instead of releasing these exact numbers from this study, if you base it on approximate answers, you're preventing p-hacking better. All right. And another application along a very similar theme showed up in Kaggle competitions. So in these ML competitions, typically what you have is some training data set that is released to everybody. Okay. And then you had some evaluation data set. Right. So evaluation data set means I train my model on this. I submit my model to Kaggle and they'll give me some number. Tells me, okay, your model is doing so well. Okay. And then, of course, there's a true test data set. That eventually you get tested on. Right. So this is for you to use while developing, and this is for the final score that gets used at the end of the competition. Right. So you do an ML model, you submit it to this thing, and then you get a score. And of course, the most attractive feature in all of these competitions is what's called a leaderboard. Okay, so leaderboard meaning it tells you, okay, who is currently leading here? What is your score among all of the competing teams right now? Okay. And this was going on for a long time, that you would submit a model, you'll get a score, you'll get a position on the leaderboard and so on. And at some point, someone figured out that you can really hack your position on the leaderboard without doing any ML model. Okay. So meaning what they did was, I'm just going to submit some completely bogus models. And based on the scores, submit a model which got 100% score. And hence won on the leader. Okay. They didn't even look at the training data set. Okay. I'm not even going to look at the training data set. I'm just going to keep submitting models. Every time I submit a model, you give me a score. You gave me a score saying 0.1. Okay. Next time I submit a model, you gave me a score saying 0.5. Next time I submit a model, you gave me a score saying 0.6. Based on this, after a few trials, they found a model which had a score of 100%, meaning they got to the leaderboard number 1. They never even looked at the training data set. Okay, and they could do this across various ML competitions. Right? So this means that this mechanism of looking at the leaderboard and so on is not like, very indicative of what the model is learning. Okay. So implicitly what happened in here is they figured out the evaluation. This is typically much, much smaller. Okay. So after this attack, what Kaggle did was they said, okay, each ID or each team can only submit one model per evaluation per day. So that was one at least sort of ad hoc way to prevent this kind of attack. But still, within 10 days, you'll probably, again, climb up to the top of the leaderboard without looking at the training data set. Okay. And so to mitigate this, there was a very nice paper by Blum and Moritz, Art, and it's called a reliable leaderboard for ML competitions. Okay. And they once again used ideas from differential privacy to prevent people from sort of reverse engineering the leaderboard rank. Okay. And the idea there was release the score with noise. Okay. And how you had the noise and so on is motivated by like, differential privacy, the models that are studied in differential. I think it's still, fair, right? Basically, you're saying I'm going to give you some noise so that you cannot hack exact, you cannot try and guess exact or cheat this specific evaluation data set. Right. So, but the noise is still random, right? So the Laplacian, let's say I'm using Laplacian mechanism. I evaluate this score and then I just add some noise and send it to that person. So instead of saying 0.1, I might say 0.11 or 0.09. And whatever you are using earlier to kind of reverse engineer the scores will not work now because I've added noise in my responses. That's a sort of procedural solution. But the problem with that is people don't know how they are doing. And it takes away this game kind of, I think leaderboard is a very attractive feature for people, right? It's, that's why people play games. You want to see your name on the leaderboard, right? And it's good to see like how you're doing across the competition and so on and so forth. Right? If you take away the leaderboard, that you can do that. Maybe not have this and just have the test data set. In the end, you'll evaluate it, but I think leaderboard is definitely something people care about. Right? And this is saying you can do that. Okay. And again, this is, it's not restricted to ML competition. This sort of thing people, I think, knowingly, or I think at least, let's say, hopefully unknowingly do it when they're building models on very small size data sets. Okay. So like, for example, let's say I'm trying to predict something, but I have very few measurements. I'm trying to build a model which predicts diabetes from genetic data, let's say. Right? How do you test it? Can you imagine something like this happening there, where I first try a model, I evaluate it, it did not do well, and then I try another model, but I'm evaluating on the same set of 1,000 people because I cannot go and sequence another 1,000 people every time. Okay, that goes back again to this adaptive data analysis sort of issues. Okay. And this is now implemented in Kaggle. So you don't see the raw score, you actually see a score with some noise. They implemented this algorithm internally so that you have this more reliable leaderboard. Along with placing constraints initially, like, you can only do one model submission per day and so on. Right, it could be that, maybe just the scale, it's just a matter of the scaling and rescaling, right? You see what I mean? Like, let's say what is 0.9 versus 0.99? It depends on the range that you're looking at. Okay. So maybe you just scale everything to be between 0 or 1. The mean is 0 or 1, and then add the noise and then go back to it. I mean, people have these kinds of attacks where they've like reverse engineered weights in a model by looking at the last bit of some output and so on. So, you have this bit tricks and things like that can also be very nasty. Right. So I think noise helps you to do away with any of that. Okay. All right. So this is for applications of differential privacy outside of privacy. Now, in the remaining 5 minutes, let me first say about one very important privacy scheme, which is private empirical risk minimization. Okay. So can imagine, we have users, which is our, x1 up to xn, and you have some labels, let's say, and then you have some curator who learns or trains a model on this and then releases the or waits. Okay. So I have my database. Now there is some company which I have authorized or I've given permission to train on it, but then the company releases the model of this. Now the question is, does this this can violate the privacy? Okay. So the question is whether you can train in such a way as to preserve privacy, which might potentially be possible because the weights that you have to learn, typically you're trying to learn under some distribution and so on, right? So if my database is big enough, potentially I don't leak information about individual entries. I just learn something about the prediction problem. Okay. And, you can really go back to our ERM setup, right? So ERM setup, we have this some loss function, parametric family, and so parametric family. And the empirical risk minimization problem that we had was we had your database X, and I want to minimize the average loss across these things. Okay. So I make a prediction on xi, compare it to the label yi under some loss, and I'm trying to find the parameters which minimizes this. So the ideal goal is to compute this argmin of the loss function. Okay. And we saw how you can use gradient descent and all the other things to try and minimize this loss function early. Okay. But this whole thing we can think of as a function of the database. It depends on the database, no matter what you run. In the end, it's a function of the examples and labels that you have. And the question is, can you train these methods in a differentially private, right? And given the importance of privacy, especially for data that you're using from everywhere, people have developed various techniques for this. But by and large, the technique that gets used the most is what's called differentially private SGD or DPSGD. Okay. This is, for example, implemented in TensorFlow, PyTorch, and so on. Along with using SGD, you can also mention the training to use a private version of SGD. Okay. And what's the private version? Any guesses for what it might be? Exactly. Right. So, you pick a start point. So what is SGD, right? So you pick a starting point and then, let's say your batch size 1, you pick a random index I and you update the gradient. Okay, so this is what you do usually. This is plain stochastic gradient descent. And in DPSGD, you just add Gaussian noise to it. Technically, you do something called clipping so that it's important for privacy. So you clip the gradient estimator and then add the noise. So you clip the large values because otherwise the privacy gets violated. And what people have figured out is how to change this noise rate to control the overall privacy of your system. Okay. And as I said, several times, typically when we think of running gradient descent, stochastic gradient descent, even if I don't have any analysis, I'm okay. At the end of the day, my model is doing well in prediction, I'm fine. Right? But for privacy, that doesn't work. You really have to show me that you're preserving privacy. Right? In fact, in the early days, people had this thing where they could make something like, let's say, ChatGPT blurt out social security numbers of some people or addresses of some people by asking some questions, right? Because it was trained on that somewhere, and by asking some other random question, you made it blurt that out. How can you guarantee that such a thing would not happen for your model? Okay. And DPSGD would give you such a guarantee. It'll tell you that if I trained using DPSGD, then my model will have differential privacy. Whether or not that privacy is enough for you is a different story, but I have a strong guarantee. I have a formal guarantee about what kind of privacy. All right. So this is something, as I said, is implemented in many different packages. And the main theory around here centers with how to choose these noise rates. Okay. Just as using step sizes is important in SGD, you would also like to tailor the noise rates to preserve the overall privacy while not hurting the convergence too much. So that's also important. Okay. So let me stop here. And on Monday, I'll say a few words about extensions of privacy to other settings. And then we'll move on to the next topic, which is unsupervised learning.